Hello everybody, my name is Difeng. I'm currently a postdoc at the University of Copenhagen. Today in this talk, I will present the work that we published at SIGCHI 2024 about metrics of motor learning for analyzing movement mappings in virtual reality. So it seems like a very complicated title, but let's try to dive into all of these keywords to see what they actually mean here. All right, the first is the movement mappings in VR. Basically, the idea is when you actually move in the physical world, we can actually map this kind of movements in different ways in VR. For example, in this case, we can have a very long finger. Basically, what you need to do is still move your hand in the physical world, but then their positions are sort of shifted in the virtual environment so that you can have a way longer finger. Basically, in this kind of scenario, it might help you with your playing some of the piano in this case here. Here's another classic example where you can have a very long arm. Basically, you still move your arm in the physical world, but then it's mapped or scaled up in the virtual world so that you can reach way further in the virtual environment. And then you can also control the third arm in this case where you actually move both of your hands and then try to control the third arm. And here is an example where you can control the whole arm movement with your finger movement. Basically, the idea is that if you want to play Beat Saber in a very constrained space where you can't actually move your physical arm, you can actually use your fingers to do all these kind of movements, and then they are going to be mapped into VR. Right? Basically, the movement mapping techniques in VR are actually helping people to complete certain interaction tasks by actually maps people's movement in the physical world in different ways in VR. Right? This is sort of part of the title. And then if we look here, there is the keyword of motor learning, and what are these? So motor learning are actually commonly researched in behavioral neuroscience or physiology. They try to describe the process, how people actually learn to acquire motor skill. This kind of motor skill can be, for example, you learn to play a piano, you learn to ride a bicycle, and then when you were an infant, you probably learned to actually grab an object in front of you. Right? So these are all considered as motor learning. And then the literature actually tried to divide it into different processes of the learning. For example, they identify that people need to do this goal selection where, for example, in the case of playing piano, you want to determine where do you want to move next, right? And then people want to figure out how they actually will complete that movement. They will have this kind of planning phase of the predicted movement. You want to predict a particular movement that can help you to achieve your targeted intention, right? And then there's action execution stage where it actually considers your whole quality of the movement execution stage, right? So when you try to learn a particular motor skill, you are likely to include improving all of these little phases in motor learning: the goal selection, action selection, and action execution. And then bring it together. Basically, we are interested in how people learn to acquire new motor skills, which is based on this movement mapping techniques, because you actually mapped your virtual movements in different ways from your physical movements, right? And then matrices are just ways for us to quantify what's the current state of motor learning. Is it good or is it bad? All right, so what are the challenges in SCI? We typically use task completion time, which is the time it takes for you to complete a certain interaction task. Can be pointing, typing, manipulation, stuff like that. And it is usually used as the only metric to measure the learning of a particular movement mapping. We know that people get better, quicker over time when they actually practice over time. Right? It is sort of predicted by this power law of learning. But actually, this metric actually shows very little information about how do users actually improve over time. Like, what are the aspects that they are improving, and what are they struggling with? Right? Are they bad at prediction? Are they bad at execution? What are the parts? Right? And how can we actually use different ways to help them to actually improve when they are dealing with a particular interaction scenario. And this task completion time does not tell us much apart from like people are getting quicker. And then when we see a lot of literature from the motor learning perspective, we see these kind of measures cannot be directly applied to HCI tasks because they have sort of very different objectives and task settings. For example, people can try to use the matrix that we call the endpoint arrow, where people see the target and then people try to move to the target. And then during the movement, they are sort of like blindfolded, so they cannot be able to see their movement. So that in this way, the end of the movement point and also the target center will be a measurement for like how accurate your prediction can be, right? In this case. But then in HCI task, we always receive our visual feedback. We can always see our hand. There's no blindfolded conditions. And then in HCI task, we always have this kind of bounded arrows where when you try to press a key, you don't have to press the center of the key, you just have to press the edge. So over time, when you learn this, you want to minimize your energy when you try to complete this movement. So in this case, it's a very different task assumption as compared to a lot of motor learning literature tasks. And then there are also varieties between different trials, where when we try to learn a particular interaction techniques, we normally have different difficulty levels and different variances levels, and then there are a lot of variabilities there. All right, so in this case, we are interested in building some of the matrices for movement mapping techniques in terms of motor learning. Basically, we get a lot of ideas from the motor learning literature. So these matrices heavily inspired by the motor learning literatures actually consider different stages for the movement. For example, the action selection and action execution. We have these two matrices are based on very similar ideas. One of them called refinement time proportion and the refinement space, which is another one. So imagine the user is trying to place a cube into the target position. In this case, the movement can be divided into the more ballistic phase, where they do a very rapid movement. A lot of people think it is sort of pre-programmed, so they quickly move into the target position. And then the later refinement phase, which considers their final tuning for actually reaching the target, right? A simple idea is that we can quantify the proportion in terms of time for the refinement phase. As they learn over time, they will be quicker, they will be more accurately predicting the initial movement without doing a lot of refinement, so that they are getting better and better, and then this refinement arrow proportion will getting smaller and smaller. Refinement space basically quantifies the distance, the equilibrium distance between the end of the ballistic movement and the end of your whole movement. Basically, what's the distance of your spatially of your first ballistic phase as compared to your final movement position. And then there's also matrices that consider the action execution stage, where it actually quantifies the distance of your movement as compared to the shortest distance of the potential movement. The idea is that users will try to shorten their distance over time, and then this arrow is going to be smaller over time. And then the normalized jerk arrow actually quantifies the smoothness of the movement. Basically, the jerk is the derivative of the acceleration. Basically, the idea is the smoothness of the movement. And then we try to put all of these matrices into different tasks to see how they will behave. The first task is the translational amplification, which is the long arm, and speed-based rotation. In this case, well, the blue outline actually represents your physical hand, then the virtual hand is the gray hand there, right? You can see it's basically based on the speed of your movement, and then basically this is an interaction techniques that people have proposed for speed rotation. And then this kind of task are called motor adaptation, where people actually adapt into a particular type of movement in VR. And then here is also where you can actually control the arm with the finger mapper approach, where we consider more about the de novo learning, which is you want to establish a new control from your physical hand to the arm. And then we conducted experiment with 16 participants, and then what they need to do is to practice this one-to-one mapping, and then in the adaptation phase, they actually learn this new type of mapping. It can be like a very long arm, and then they come back to the de-adaptation, back to one-to-one mapping, right? And then readaptation, they learn the new mapping again. Basically, the switch between the one-to-one mapping and the new mapping that we asked them to learn. And then here is the result. It seems also very complicated, but then all the idea is that all of the matrices that we try to get from the motor learning literature are also having this kind of behavior like task completion time, where they start with the faster initial learning followed by more gradual improvements over time, right? Overall, it sort of follows this kind of trend. As you can see, which we try to approximate with the power function here. But then you can actually see some of the differences here. But then if you refer to our paper, we actually infer the idea is perhaps people have already learned to move in an optimal way, which here is the normalized path arrow. They've already find the optimal path for movement. So when they second time do that kind of one-to-one mapping, they don't have to relearn the whole thing again, right? This is our inferences, but then you can refer more on this in our paper. And then we also see for different tasks, speed-based rotation, which is a difficult task because people have to do this kind of mental rotation. And also for controlling the arm with the fingers is more difficult mapping. We see lower R2 values, perhaps because the learning is more difficult to capture in all of the scenarios. And then we also see this kind of matrices capture learning behavior when task completion time cannot. For example, in this case, I believe this is one of the cases in the second task where you do this kind of rotation. We can see that people are still learning in terms of the refinement space. So basically their prediction is becoming more accurate. Perhaps they are also improving a little bit on the path arrow. But then if you see from the time here, it's actually going up a little bit, which could be due to the fatigue effect. But then you can also refer to more of our justifications in the paper. And then what can this help us? Right? First, it can help us to identify motor learning, right? If there are learning process going on, then it must be related to some kind of mental or motor costs like cognitive load, memory resource, attention fatigue, and stuff like that, right? We cannot ignore this when we are designing interaction techniques. And then it can also help us to determine the source of learning. What are the, for example, for different individuals, people seem to learn in very different ways, right? In this case, one participant is improving very quickly on the path arrow. They are able to quickly find the path arrow, but the other will take more time to actually understand how to move optimally. One is improving on the jerk, basically try to make the movement smoother, but while the other does not seem to provide a very clear trend. Because it can help us to determine the source of learning, we can better understand how can we actually help people to be better at a particular interaction techniques that we introduce, right? They probably necessitate different methods to facilitate their learning. And then it can also help to inspire different techniques, basically optimize the learning curve. For example, if we know that people are optimize a particular movement to try to find the shortest distance, can we just display the optimal line of the movement so that they can just follow along, or they can follow basically sort of help them to predict how to move in the shortest distance, right? There are different ways like expert demonstration, dynamic target location. Basically, we know the arrow that people will produce during their prediction phase so that we can move the target dynamically to the target position so that people can actually reach them without doing much more correction, right? These are all the different ideas that can be able to get from this new matrices. All right, if you want to find more interesting materials about all of these matrices and all interesting results, you can actually refer to our paper. And thanks for listening.